the electric potential at a certain point A is voltage at A, and the electric field at this same location has a magnitude of electric field at point A. The electric potential and field at some other point, VA and VB, or VE, VB, EB, both potentials are measured with respect to the same reference point. Okay, so that's reasonable. And we know that the voltage or potential of A is greater than potential of B. Consider the following statements about the situation, and they give us some statements. All right. So we have electric field comparison. Okay. So there are basically two examples that I use when we're talking about electric fields and voltage. So the first example is a parallel plate capacitor with a battery. So this is a battery, we'll call it 100 volts. And so it would charge this plate up to 100 volts. Potential is the exact same thing as voltage. So whenever you see the word potential, think voltage. Yes. So 0 volts, and this is going to create an electric field, specifically a uniform electric field going down. So this is particularly useful when you're trying to think of equal potential lines, and so it's like 75 volts, 50 volts, 25 volts going down. It's going to go down linear. So basically, the closer you are to the 0 volt plate, the lower your potential is going to be. So this is really useful when you're talking about electric field lines and equal potential lines. The other one is a hill. So we're going to draw a hill that looks like this, just like that. So we're going to have a ball up here. This will be A. We're going to have a ball down here. This will be B. And when you think of electric field, you should think of force, because force equals QE and vector lines. Also, when you think of voltage, I'll put little bars up there just so we can think of it in terms of voltage, not velocity, because it's both V. We should think of work, because potential energy, which some people write as big U, some people write as E subscript P, is Q. I'm going to write this as delta V, because voltage is always a difference. Sometimes the comparison point, reference point, is infinity and it's considered to be 0 and therefore ignored. But the reality of the situation, always a difference. Sometimes the difference is being compared to 0. Okay, game face. So what they tell us is we know that the voltage A is greater than voltage B. What that means is, in terms of this ball analogy, the gravitational potential energy, or potential energy times mass basically, but potential energy A, the ball A is higher than ball B. And the force, basically the force pulling it down, the net force pulling it down, is going to be the equivalent to the electric field. So that would be the slope of the hill. So the formal definition, more formal definition, a formal definition of voltage is negative E dr, and it's a dot product. This is the path, and the dot product of two vectors gives you a scalar. So electric field vector and voltage scalar. And so all that this VA greater than VB tells us is that ball A is higher than ball B. That's all that tells us. And everything else is just kind of fluff to give you the scenario. Nuance and detail so you can draw the scenario correctly. All right. So we're going to use this version right here just because it's going to be easier to visualize. So now we're going to look at electric field at A must be greater than electric field at B. So no, what that says is the slope of the hill at point A must be greater than the slope of the field at point B. So we could use the analogy or example of two conductors And we could come up, like with parallel plate capacitor, electric field, we could make that work. We're not going to, but this in both analogies would work. It's just going to be easier with the left one. So this says the slope of A must be greater than the slope of B, and that's not true. So I'm going to take my ball B, put it up here. I missed a little part of B. There we go. There you go, little guy. I should have grouped them all together. Hop, 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 hop. And group. There you go. Hop. Come on, A. You're also going to get grouped. All right. So the slope at B. So the slope at B is greater than the slope at A. Therefore, that's just a counterexample to show that that is not necessarily true. It totally could be true, where we could have B down here and A here, as long as A is higher than B. So there's almost zero relationship between voltage A and B, one being bigger than the other, and electric field A and B being bigger. It basically just means the slope of the hill here. So voltage equals negative integral, formal definition, electric field, slope of the hill. Okay, so that is false. Then let's look at the second one. Electric field at A cannot be zero, not true. We could be at the top of the hill right here, in which case the slope would be horizontal, which means the slope would be zero. Rise over run is slope, change in y over change in x. So the change in y is zero, slope is zero, electric field, using this analogy, is also zero. So also false, both A and B must be non-zero. That's not true. A could be at the top of the hill, B could be in a little valley right here. It could be that neither of them is on a incline or a slope. Therefore, they could both, the electric fields could both be, both A and B must be could both be zero. So, and since we said EA can be zero, the false to that, this also kind of automatically makes 3 false as well. So this would be A. None of these statements are true. So that's how I'd approach this one. 2 analogies. Parallel plate capacitor, which is good for electric field lines and equal potential lines. And then the hill analogy, which is really useful for looking at the relationship between electric fields and potential. Potential is related to work or potential energy, and electric fields are related to force. In this case, it is the slope of the hill. Hope that helped. See you next time.